Okay, question 6 is about sound. So we've got a teacher. So there's the teacher. Here are the students. They're going to fire a gun. They've measured this distance to work out the speed of sound. Clearly there's going to be a bit of an issue here in terms of reaction times of students and things like that, but we will know that they will get a rough idea of what's going on. Clearly you're usually asked about the distance. If you've got to do it this way, which is a bit ropey, make this distance as long as you can. If you're ever asked how to improve it, let's have a microphone here, and a data logger in between that can do the time. So that's that just gone over as a general practical. So the next one is the students obtained a book value of 240 meters per second. The accepted value is 343. Calculate the difference between their value and the accepted value. So in maths, you've learned it's whatever the change is divided by the original amount, and it wants the percentage difference times 100. So change over original times 100, and we're away. So the change, take the two numbers away, 343 take away 240, divided by the original, so the book value is this, 343 times 100, and we've got 30.0. When the distance was 100 meters, the students measured this, so we can see they vary quite a bit, which you would expect. Why? Well, they've got different reaction times. Actually, let's do it. Different reaction times. What's this going to do? It's going to add systematic error. So we've got random error, things due to temperature changes, slight difference in conditions as we run the practical. And then there's systematic error where we've not designed the practical as well as we could in terms of how we take our measurements. And as I said, we could have used microphones and things like that to improve it, which comes up in a second. So why do their times vary so much? Human reaction times, 1 mark, have added systematic error to the results. How might we improve this experiment? Increase the distance, that will lower the percentage error from human reaction times. A really nice one is use microphones with electronic timers. This completely removes human reaction times. So the one just reduces the percentage error, the other one gets rid of that error. Next one, we've got a sound wave coming from a loudspeaker. So we know that sound waves are longitudinal waves, and I've taught you V, P, DOET, so longitudinal waves. If that's the direction that the energy goes, the vibration will be parallel to it, or oscillation, vibration, oscillation. It says draw and label the distance of one wavelength. Now it doesn't matter. So what we've got set up here is a compression, rarefaction, compression, rarefaction, compression. As long as I go from compression to compression or rarefaction to rarefaction, that is one full wavelength. So I've just got to go to a place where it's bunched to a place where it's bunched, or a place where it's not bunched to a place where it's not bunched. What the hell did I pick? I picked bunched to bunched, compression to compression. Describe the motion of the particles as they travel through the air. So we've got this idea now. Tell us about a longitudinal wave. So we're going to talk of vibration and movement backwards and forwards, and that it's parallel to the direction that the energy went. So the energy is coming out this way, and the vibration is parallel to it. So the particles vibrate forwards and backwards, parallel to the direction of the energy transfer. Just remember that memory method there. End of question.